So no cussing.
Oh, man.
Little potty mouth.
You tell yourself. Shenanigans. Man.
Tell me to be more happy. All right, so we are starting off with net ionic equations. Net ionic equations, okay? Some big things for this part of the lesson is having a better understanding of what aqueous means and what dissociate means. So I'll let you get those written down so you can listen. What?
We get to write that stuff down and then you talk. That means that we can pay more attention.
So you're saying I should have signed this for homework before the lesson?
No.
So you can come
You're
in.
You're twisting
the
our
opposite
words.
of what I'm saying.
That's exactly what you're saying.
No, I'm saying.
Here we go.
Just stay
So-
quiet.
When we say that a compound dissolves in H2O, what we really mean is it dissociates in H2O, okay? Because when I say like you pour an acid on your hand and it dissolves your skin, that's different. That's an actual chemical change than if we put salt and water and it dissolves. Everybody see how dissolve is used slightly differently? What we really mean when salt dissolves in water is it dissociates in water. Okay? So when we look at this, we're going to put what I have in this container right now is water. And what's going to happen is we're going to put our sodium chloride, our salt, in the water, and we all know that it's not going to dissolve. It's going to dissociate. Okay? What dissociate means is it's going to split into its ions. Well, somebody give me one ion of sodium chloride.
Sodium.
Chloride.
Chloride negative.
Positive.
Say it again.
Last three.
Chloride negative.
Chlorine minus 1.
Oh.
That is one ion. What's another ion of salt?
Sodium.
Sodium plus 1. Remember, an ion is an element with a charge. So all of you that were saying chlorine, sodium, those are elements, not ions. Okay? So when I say that dissociation means it's going to split into its ions, what is going to happen to this compound?
They're gonna split
It's
up.
going to split.
Divorce.
So isn't that something? That's not the same thing?
Yes. That means that sodium is soluble in water. That means sodium dissociates in water. All right? So what happens here is we have H2O. And in the covalent unit, we learned that molecules can be polar or nonpolar, right?
Yeah.
Water is what?
Polar.
Which means it has a very negative end and a positive end. Well, if we look up here, the negative end attaches to what part of the positive end of that compound, and the positive end of the water attaches to the negative. It's like a battery or a magnet. Positive attracts negative.
Okay.
Okay? And that attraction is what pulls that apart. That makes it dissociate. So, what we can say is, because this dissociates in water, this is an aqueous solution. So does aqueous mean liquid?
No.
No. Aqueous means that will dissociate in water.
Anything that dissociates is
Anything that dissociates in water is what we call aqueous or soluble. Yes? Kind of that's huge for today. Okay? So, when we get to maybe a little bigger example, we are specifically with net ionic equations, we are specifically talking about double replacement reactions because we check solubility, right? So what type of reaction will occur right here? Because of AB plus BC, and you should be able to predict the products, right? And if you can't, that's an eagle's nest where you can come and talk. That was a different lesson. That's not what today's about. So when I add that to this, I should be able to predict the products. However, the new step for today is you're going to have to check solubility for all of the reactants as well. Everybody got that? So, 30 seconds, check solubility for these two things.
No, I'm talking about the tape.
There's some,
No,
Some that are not there.
I'm talking about like that.
It's not there. On the
Just go in the back
packet.
of the packet.
I don't know.
It's not in the packet, that's what I mean.
All right. Yes, Aiden.
Oh, they're both aqueous.
You're saying they're what?
I'm saying they're both aqueous.
These are both going to be aqueous. Okay? Good. Well, what does that actually mean? So in third grade, you saw that salt dissolves in water. You could go home and say, Mommy, I learned that salt dissolves in water today. Today, you can go home and you can say, Mommy, actually, it dissociates in water. It dissociates in water because, listen, because if I look at chlorine and iron and I put it, and I know that it's aqueous, how should I draw it in the container? Together or split?
Split.
Because it's
Aqueous.
aqueous means it dissociates. Dissociate means it splits. Fe, and there should be 2 chlorines. So I could present that as being split up, showing that it dissociates in water because it's aqueous. So what would I do with a K2S?
The same thing.
Split it up because it's aqueous, okay? And there should be 2 of them. All right? So now we're adding 2 aqueous solutions to each other to see what happens, right? So now here is where you should be able to predict the products. And when I say predict, I don't mean just like come up with some random prediction that you have no idea about. I mean you should actually use your rules for double replacement and come up with the right products. And that's what you should get, right? And from here, you also should be able to tell me solubility. Isaac, KCl. Yes, what? Soluble, which makes it what? Aqueous. Jacqueline, FES. Okay, so use it now.
Okay, wait, no, this, yeah, it's soluble.
It's soluble. Find sulfide. Not sulfate, sulfide. What title is it under?
Insoluble?
Insoluble, right? Is it paired with an exception? No. So what is it? Which makes it a
Solid.
It's wrong to yell out yes when I'm talking to. So yes, that's how you use the chart. It's solid, right? So when I go to my big beaker here, right, Clay, how should I draw my KCl?
Separated.
Clay, how should I draw my KCl?
Separated.
Some of y'all need reminders of how to be in a classroom, okay?
Yeah, people.
FES, FES. How should I draw it, Larry?
Together.
So, what am I trying to tell you? Your aqueous solutions split up. Your solids do what? Stay together. And when I click through this, that's exactly what all of this is doing. Now, those of you that really paid attention to the lab, what station was like this? Station number 4. right? Where we added the 2 clear liquids. Now listen. When you're asking the question, Holly, of do I write the products or do I write like what's produced, or produced and products are the same thing, right? So when I said do you like write the substance or the formula, what's being produced over here as a solid? FES, right? So when you're in that group, your solid thing that was made, you should have been able to predict, right? Before you even did it. So next year we're going to do a little bit better, where you're going to go through all of, not you, but my kids will go through all the stations and predict all the products, and they should be able to say, okay, in this station, I'm going to get a solid. In station number 7, who remembers what station number 7 was?
It does nothing.
Is it?
So if you would have predicted all that stuff before, I wouldn't have people this close to the reaction trying to look at it, right? Because you would have known
That was me.
nothing's going to happen. You see what I'm saying? You would have known what was going to happen before it happened.
Yeah.
We were running an experiment.
No, I get it.
Yeah.
I get it. But y'all were,
But that was wrong.
which is a good thing. That means you're engaged. But you would have known before that nothing was going to happen.
Yeah, because the activity.
Now, here was the most frustrating question I had through every class. You ready?
What?
Well, what do we call this? Don't say solid.
Iron.
A precipitant.
Oh.
A precipitant is a solid formed from 2 liquids. If you didn't know that, which was about half of my kids, I'll write that down somewhere for the 3rd time this year at least. Okay, good. And you should. You should, because we talked about it before a couple times. But I had a lot of kids that did not know what precipitant was, because that was something that you could circle. If you did not see a solid formed, and some people put precipitant for the station number 1, there was no solid there. Like no solid was being formed, other than what the little metal strip you threw in. But that was becoming less and less, and it eventually dissolved out of nowhere. I mean, into nothing. Even though not nothing because conservation of mass. But the precipitant definitely was not formed there. Okay? So this is important for how we get our net ionic equation. So here are your steps to doing this. And just like every other thing that we've learned this year, I tell you that the steps, the rules, doesn't make a lot of sense until we do it. But here they are. Right? Write your balanced equation. That's nothing new. We've done that 100 times. Complete ionic equation. This is where you're going to put in your aqueous and your solid or your liquid or your gas, whatever's being formed. Number 3 and number 4 are what's going to be brand new to you. You're going to cancel out spectator ions, and then you're going to fill in, you're going to complete your net ionic equation by taking out those spectator ions. So, the big vocab word today is spectator ions. What is a spectator ion? Well, a spectator, do they get to play in the game?
No.
Think about that. They're not involved in what's being produced. They're there watching for some support, but they don't do anything necessary for the reaction to take place. That's what a spectator ion is. For those of you that were writing down, hopefully you got that. Maybe added 1 or 2 extra things there. So, this is the steps you need to take to get to the final product. Okay? And I'm going to tell you, like, this is the hardest it's going to get. Are you ready? I give you a word problem. Y'all need to follow this real quick. Because this is how you're going to have to do it, like on a free response on your test. Back page, turn there, you got to do one of these. This is how you do it. I give you a word problem. From there, you need to give me a molecular equation. That's what you've done before. That's what our last test was over. Does that make sense? Like that's just normal stuff. Balance it out. Make sure the subscripts are good. That's what you've been doing for the last month. Okay? From that molecular equation, you should be able to give me the complete ionic equation. That'll be new for you today. You don't know what to do with that yet. Question?
Where we at?
I don't know what page we're on.
So we are on page 2.
H2.
Okay? Then from your complete ionic equation, you're going to come out with a net ionic equation. Once again, you don't know how to do these two yet. That's what we're learning today. You do know how to do this one. So from silver nitrate combined with sodium chloride, what type of reaction is going to take place? Double replacement. So you should be able to write reactants and products and balance it, no problem. No, I'm not saying no problem, but you have the skills to do that. Right? That's what we just did there. The only additional thing that you need to do now is put in solubility. Does everybody see that? You will have to check solubility for each reactant and each product. There's a reason for that. Not too bad. Here's your solubility chart. That's nothing new either. Right? Now use your solubility rules to decide what dissociates and what doesn't, and write a complete ionic equation. And here is that complete ionic equation. Don't freak out right away. I'll explain everything to you. What we're going to do, what happened in the beakers to all the aqueous stuff? Dissociated and did what?
Split.
Broke apart. Well, guess what that line is showing you?
Split.
It's splitting apart. I call it the dissociation line. So what you're doing is you're splitting every one of your aqueous things as it would be in solution. You're splitting it into its ions. So do you need a charge there?
Yeah.
It's an ion. You need a charge. So we split up that one, we split up that one, we split up that one. Why did we not split up AgCl? Solid. Not too difficult, right? Like, just as long as you're listening, you're good. This is your complete ionic equation with your dissociation lines in it. The only extra thing you're doing here is splitting up aqueous, adding the ions, adding the charges. Yes? From there, now you need to know what a spectator ion is. A spectator ion is an ion that appears obviously on both sides of the reactant in an aqueous solution. That's like the key part of that definition. A spectator ion appears in an aqueous solution on both sides of the equation. So how do we find those? Well, first, Ag, is it aqueous? In an aqueous solution? Yes, it is. So, is it in aqueous over here?
No.
So can I cancel it out?
No.
No. Nitrate,
Yes.
aqueous on this side, aqueous on this side.
Yes.
Can I cancel it out?
Yes.
Yes. Cross it out. Sodium, aqueous on both sides. Yes, cancel it out. Chlorine,
Nope.
aqueous on both sides.
No.
It is not, so I need to keep it.
Yes.
So that's what we did for number, was that 3? Cancel out spectator ions. Once again, we canceled out the spectator ions. There you go. From there, write the net ionic equation. What you're doing, if you want to rewrite this, write what's left over. With charges. Ag plus, bring it down, Cl minus, AgCl.
It's like a synthesis equation.
This one is like a synthesis, and they're not all going to look like that. Most of them will, but the next one won't. Okay? You just write what's left over. So it's not like you don't have to think about doing anything else. You're just like, okay, cancel all those out. What do I have left? Write it down.
So we don't have to like cross charges or anything.
Nope. Nope. No. Just write what's left over. It's as simple as that. Yes?
And you say we have to write the balance equation like with the coefficients, right?
You'll find out that those cancel out as well.
Oh, okay.
Those will all cancel out. Yes, Holly?
Is it always going to result in a synthesis equation?
No.
Okay.
Most will. The next one doesn't. That's why I said that. And out of all the examples that we do, it's the next one. The rest of them pretty much do. Now, this is not a synthesis reaction. This is just stuff that is pulled from the double replacement. So this is still a double replacement reaction. Okay? Why do we do this? We do this because it shows us what elements are actually doing the work to get what we need. How does this work in the real world? This is a product, that solid is a product that somebody can sell or put to another product and they combine to form something. So if you know anything like about business, like a car, one business doesn't make every single car part, right? There's different businesses, like there's a business out there that makes ball bearings and that's it, right? They specialize in one thing, right? So this company might specialize in extracting that from certain materials, right? So what they need to know is how much of silver and chlorine they're going to need to make a certain amount of product so they can sell it. It's business, right? You need to know every detail about your business if you want to make money, enough money. Okay? So that's how this is used in the real world. So here is your next example. Once again, I need kind of 3 separate equations here. Complete molecular, which is given to you.
Molecular.
This is the molecular equation. I need you to give me a complete ionic equation and a net ionic equation. So, the good thing is, I've already done solubility for you as well. What's the one funny thing up there that we haven't really seen yet?
Gas.
A gas, and it's on what side?
The product.
The product side, but what do we also see in the reactant side? A solid. Usually they're both aqueous, right? A little side note that you need to know is that if it's going to be soluble, anything that's soluble is going to be aqueous. You already know that. Anything that's insoluble could be a solid, could be a liquid, or could be a gas. So if a gas is formed, will this double replacement work?
Yes.
Yes.
That's insoluble.
Exactly.
I need an insoluble product for the reaction to occur.
Oh, okay.
The only time a double replacement will not occur is if both of them are
Solid.
Yes.
Oh, okay.
Are aqueous?
aqueous, which means it's soluble.
The last one's both aqueous?
What?
The last problem we did, they were both aqueous.
The products. For the reaction to occur, one of the products has to be insoluble. Which means now, before you thought it was only solid. Now you know it could be a liquid, it could be a gas, which also tell you why neutralizations always work. Because it forms a liquid of water, which is, we can think of as an insoluble. Okay? So, when I do this, I need to next do my dissociation lines. I need to split up all my aqueous. So, HCl, will it be split?
Yeah.
Yes, it will. Plus, minus. Z and S,
No.
will it be split? I mean, solid. H2S.
Wait. No, you don't split it.
Nope. Charges above it.
Oh.
Trying to trick us.
Oh my gosh.
Man.
You all paying attention?
Yeah.
Good. Zinc chloride.
Yes. Yes.
Okay, there is your complete ionic equation. Questions?
You forgot to add the G.
The what?
You forgot to add the G and the H and the
Why? Yeah. Sorry. Yes, Larry.
Do we still need the subscripts after we split it up?
Yes. Yes.
So CF still needs it too?
Yes. Okay? Now what do we do?
Wait, wouldn't it be two negative?
Cancel out.
You see which ones are.
What do we call that?
Spectator.
Spectator ions. We need to cancel out spectator ions. These are the ions that appear in aqueous solutions on both sides of the equation. So, hydrogen, yes or no?
No.
Chlorine.
Yes.
And if we would have balanced this before we started, there would have been a 2 right here, which means how many chlorines did we cancel out? How many chlorines did we cancel out?
2.
So it makes sense. If you balance this stuff right and you cancel out your ions, you'll be canceling out the same amount on both sides. Yes.
Do we have to balance it? Or
You will balance it before. Yes.
what about the hydrogen too?
It's two over there.
There's two over there. But you don't.
Yeah, so there's still 2 H's right here. Yes. Right? Do I cancel anything else out?
Nope.
Nope. So now I'm bringing everything down that's left over. I have 2H plus zinc sulfide. That produces hydrosulfide acid. Sulfuric acid. Hydrosulfuric acid. It's a gas. Plus zinc. A zinc ion. Here is your net ionic equation. Yes.
So, like, at the end, as they're by themselves, do you put the charges?
Yes. Notice how did we break these into their charges? The solid and gas. Bring it straight down. If we broke it into its ions, just bring it everything straight down.
That's the charges?
Yes. So, what happens if you forget the charges on the test?
It's wrong.
You'll get 1 off. Okay? Because you know these will be worth multiple points, right?
What's the test for this?
The 20 is 28 to 9. Questions? Okay. Try this one on your own. Those will always be solid. You're looking at all this as one compound. So nitrate is always, anything paired with nitrate is always going to be. Sorry. Mhm. Mhm. Yes.
But I wonder, I have to go back and like, do this to the ones that like, couldn't do.
Mm-hmm.
But are they like, where they can't form a product? If I did that.
There's just only a few of them that don't form a product. If they don't form a product, you can stop right there. So here we go. Of these 4 compounds, what's my only solid, Zane?
What I like to,
These are the,
BA and SO.
there you go. So here's your only solid, the rest are gonna be aqueous. What do I need to do to balance this, Carson? Sorry, Aiden.
Oh, yeah, so you have to split all the aqueous ones.
Balance the entire equation.
Oh, right, so you have to add a 2 to the sodium. Right, you have to add a 2 to the sodium nitrate.
So I'm balanced. I got solubility up there. That's a good molecular equation. What's that? Now I need the complete ionic equation. So now what I'm going to do is go through and split all my aqueous stuff. Aqueous. And then I'm going to put their charges above them. Plus 2 minus 1. Yeah? Notice how I left the solid alone. Once you figure out that that's solid, it stays put all the way through everything. So now I need to do what?
Do the
Can't do it with
ionic
the-
equation.
Spectator ions get crossed out. Sodium,
Yes.
see it. Sulfates,
No.
barium,
No.
nitrates.
Yes.
Which leaves me with, rewrite the stuff that you have left, SO4 minus 2 plus Ba plus 2
Barium,
gives me,
barium, sulfur.
there you go, and that'll form a solid.
So do we only write like the little, S thing on the products or the reactants too?
I'm mainly worried about your solids. Because I know that these came from, if you want to write aqueous down here, that's fine.
What is that formula called?
So we started with your molecular formula, or equation. From there we got our complete ionic equation. And now our final step is the net ionic equation. Net is after we've canceled everything out. Like what's your net income after you've taken taxes and all that kind of junk out? Like what do you actually bring home?
Okay.
That's what we're,
So like what we're trying to get.
right. What are we actually using in this equation to get the solid product that we desire? Okay? That is how you find net ionic equations. Not too bad?
No?
Most of my kids have said it started off like, what are you doing? And now it's not bad. Okay, then do it on your own. Okay, so here are a few questions that I could get from this, like just more than just saying, hey, write all this stuff out and give me an answer, right? The first question is, give me, of your reactants and products, give me one aqueous compound.
You want us to give it
Sebastian, give me one.
K2CO3.
So K2 potassium carbonate, right? Now, on your answer choices, I might say potassium carbonate, which means if you don't know how to go from the formula into the name, that could be a problem for you, right? Back to unit 3. Yes? And you need to know how to find solubility. Kind of a two-step thing there that you all have the skills for. Okay? Give me another aqueous. Connor?
Aqueous. SRCO2.
Which the name is
That's strontium oxide. Or chloride.
what? Strontium chloride. You see what I'm saying? You need to be able to name these things. Now, give me a solid product.
Strontium carbonate.
Strontium carbonate. Yes? The other one is, give me the list of spectator ions. So what am I asking for?
The ones that are gonna be crossed out.
The ones that are being crossed out. See what I'm saying? Not difficult, but if you need to be thinking of all these different ways, I can get a question out of this stuff. So look at all the things you crossed out. Either one of those or all of those will be listed in an answer choice. That's what you choose. Not terrible? Are you sure? Okay, so somebody give me a spectator ion.
Okay.
Potassium.
Potassium. What else?
Chloride.
What else? Is that it?
Yeah.
There you go. It should only be 2, because the other 2 make up the product, the solid product.
We put the charge,
Yes.
that's the charge is in the,
Spectator ions. If I'm asking for an ion, I need a charge.
we put the charges in the,
Product?
yeah.
No, because you should never broken them apart to begin with. Yes.
And then that equation, whenever they're by themselves, do you put like aqueous?
You can, yeah. I would. Specifically the solid or the insoluble, you need that label on it. Right? Okay. So that's net ionic equation. Let me get this